Hello, how are you? How are you doing? It's me, the pioneers in methods, the researcher, the Tunisian mathematical researcher. Today or this night, we are going to focus on the solution of 19th degree polynomial equation. We'll try to solve, of course, this 19th degree polynomial equation. We'll go step by step. Okay, so be ready to join your lecture and to be benefit from let's say solving a 90 degree polynomial equation. Okay, now I'm going to share the screen with you so that you can see the whole lecture. Okay, so let's focus on first I'm going to okay to share the screen so that you can be benefit from the course. So you can see here my colleagues. Here we have as an introduction the 19th degree polynomial equation solved exactly. A final word against Abel's theorem, meaning that this method or this EMST approach is in fact a final word against Abel's theorem. Why? Simply because Ruffini theorem closed this door and told that it's not possible to solve polynomial to the power 5 or higher. Okay, so in 1824, Niels Henrik Abel etched his name into the mathematical canon by proving what became known as the Abel-Ruffini theorem. Let's see what states this theorem. So this theorem told that there exists no general solution in radical for polynomial equation of degree 5 or higher. For 2 centuries, the result was accepted as an intellectual closure, a declaration that symbolic solutions to high-degree polynomial equations were fundamentally out of reach. Abel's theorem did not merely identify difficulty; it closed the door on the possibility of exact formulas for degrees beyond 4. Mathematicians turned, in fact, instead to numerical approximation, perturbative method, and iterative solvers, all of which suffer from instability, rounding errors, and an inability to provide exact algebraic forms. But you can, let's say, uh, believe that that door has now been opened again, and the one who opened this door is named Murad Sultan Ezouidi, not through contradiction but through transcendence. In 2023, Murad Sultan Ezouidi introduced a breakthrough method, a new symbolic theorem, now known as Ezouidi theorem or Murad Sultan Ezouidi theorem, which bypass, in fact, the constraints imposed by radical by using recursive power sums, complex exponentials, and deep recurrence structures. The Ezouidi method achieves what was once thought mathematically impossible. It delivers exact, simple, closed-form solution for polynomial equation of any degree. This book, the 49th volume in the Ezouidi series, presents the complete symbolic solution of a 19th degree polynomial equation achieved entirely through Ezouidi theorem. This solution is, in fact, algebraically precise, involves no numerical approximation, and stands as direct evidence that Abel's impossibility results does not apply to Ezouidi framework. Abel's theorem concerns radicals. Ezouidi approach surpasses them, means that we give exact symbolic roots. We never make approximation. Okay? So here I will ask you a question. Why is Ezouidi theorem closes between parentheses? Why is Ezouidi theorem closes the door on Abel's theorem? Let's see here in the first column we have aspects, degree limits, and root 4. And in the second column, we have classical method, Abel's numerical. And the third column, we have the theorem of Murad Sultan Ezouidi, or Ezouidi theorem. You can see here, degree limit, let's say the method or classical method, fails for n is more or equal than 5. If we compare these two, Ezouidi theorem, solves any degree. Let's see, for example, we have n equal 19 means polynomial to the power 19. We'll see after how we'll solve it. Okay, using the Ezouidi theorem. Roots form for Abel's and classical method, approximation or radical. Only for n is less or equal than 4. For Ezouidi theorem, we have exact symbolic expressions plus complex exponential. Okay, then we have numerical for error handling, numerical instability, and rounding errors because they make a guess for the first root and the work, let's say, depends on this guess. Okay, so here for Ezouidi theorem, zero error, purely symbolic precision, and for generality limited to specific solvable forms for classical method and Abel's numericals method. But for Ezouidi is universal this theorem via recurrence and structures. So let's conclude here. Let's conclude details. Okay, details are hidden while you're sharing screen. Okay, I'll check here. Okay. So we continue with all that. Now let's conclude. Okay, we can say that the equation solved in this book, in fact, is more than a mathematical result. Okay, it's a fact. It's a philosophical statement. The Ezouidi theorem does not contradict Abel's theorem, but it transcends it by opening in a rich symbolic space where solutions are derived not from radical but from structural recursion and exponential form. Okay, it renders obsolete the idea that high degree problem equation must rely on numerical guesswork. Okay, through my EMST approach, we will see how we derive the exact symbolic roots and not a guesswork. Okay, we never, let's say, make iterative method, right? Choosing one route and we'll check if it work or not. Okay, and we'll depend on it. No, okay, this is the for method. So it outperforms both classical and AI systems which falter in the face of complexity, instability, or the absence of general radical form. Thus, this 49th volume stands as a milestone. Okay, a 19th degree problem equation solved exactly, symbolically, and rigorously using Ezouidi theorem. And with that, the door that Abel's once closed has been opened permanently. So let's see here. Today or this night, we are going to explore a method that completely defines how we solve high degree problem equation using Ezouidi theorem. This method allows us to derive the exact symbolic solution for polynomial equation that traditionally pose significant challenges. We will be solving a degree 19 problem to demonstrate or to prove how Ezouidi theorem works, and we will compare it with the classical numerical method to highlight the power of this approach. For the comparison, in fact, for Newton and Abel-Ruffini classical method, they will never succeed to give the exact roots. Okay, even for the root theorem, okay, also will never ever give exact roots. Okay, here let's begin by examining the polynomial equation we are working with. Here is our degree 19 polynomial equation is in front of your eyes. You can make some notes. You can write polynomials, its coefficients, and so on. So the polynomial p of x is in fact equal to x raised to the power 19 minus 19x to the power 18 plus 171 x raised to the power 17 plus minus 969x raised to the power 60 plus 3,876 x raised to the power 15 minus 11,628 x raised to the power 14 plus 27,152 x raised to the power 13 minus 50,388 x raised to the power 12 plus 75,582 x raised to the power 11 minus x raised to the power 10 minus 831,392 x raised to the power 9 plus 4,081,383 x raised to the power 8 minus 11 million and 34,852 x raised to the power 7 plus 19,372,038 x raised to the power 6 minus 23,267,376 x raised to the power 5 plus, of course, here 19,395,294 x raised to the power 4 minus 11 million and 84,271 x cubed plus 450,679 x raised to the power 4 plus 4,156,794 x squared minus 100,000 x minus 73,375. Okay, so this is the polynomial to the power of t, and this polynomial has been written in its standard form, like x raised to the power 9 minus L0 for the q x raised to the power 18 plus L1 for the q x raised to the power 17 up to negative 18 of the q, where here the coefficient L0 in fact is 19, L minus 1 no need to write because it's going to be 1, L1 is going to be 171, and for example L4 is going to be okay. Okay, so here now let me show you how Ezouidi theorem solves this polynomial equation exactly. We begin by expression. Let's say the polynomial as p of x equal x raised to the power 19 minus L0 for the q x raised to the power 18 minus L18 for the q. Okay, here the polynomial here is the polynomial we are solving this night. As you can see, it's a 19-degree polynomial equation. A traditional method would rely, in fact, on numerical approximation, but we are going to approach it systematically using my theorem. First, let me point out something key. Here we have sigma k from 0 to 17 is equal to a 0 for q plus xk that go through 0 up to 17 divided by 19 simply because the highest power is 19, and the last root just put k equals 0 and obtain this one is a clear 19 plus 0 divided by 19 has to be equal to 1. Okay, means this polynomial can be factorized as x times polynomial to the power 18. Okay, first of all, let's share this one. I will try to share it first. Okay, go to YouTube first. I will share it to on Facebook. It comes here. Go to your channel. Okay, comes here if it is possible. Yes. Now I will share this one first. So it works now. I'll check how it works now. Okay, it works. I will share this first. I'll check how to share it works. Yes, I will share this section. I will share, yes. I will share this first, then we continue. How to share it works. Yes, I will share this section. I will share, yes. I will share this first, then we continue. Share Xor. Join me. Join me now. Join me now. Okay. خلاص, I'm going now to share this one. Okay, on Facebook. So I already shared this. I will share this section. Okay. This is no need. I will close this one. No share, yes, no need. I will share this first, then we continue. This is streaming. Okay. Join me. Okay. We told that we continue. We continue. So here we start with all that we told that the exact symbolic roots of this 19th degree problem equation, in fact, are written as the following: sigma k from 0 to 17. We can here add to 18 because we exclude 1. We put that k equals 0, okay, to obtain, let's say, the first root, which is clear. 19 plus 1 divided by 19 gives 1. This is its trivial root, okay? Now here we have this explanation should in fact provide a solid understanding of the challenges classical method face when solving high degree problem equation. Okay, so polynomial and how Ezouidi theorem offers a promising alternative. My method based in fact on Morat-Sultan's theorem excludes all classical methods, including Abel's theorem, which states that certain polynomial can't be solved using radical. Contrary to Abel's assertion, my method demonstrates that even polynomial with radical roots can be solved exactly where traditional approaches fail. My theorem reveals the exact symbolic roots through a structured process that bypasses the limitation of classical algebra and numerical methods. This is not, in fact, just a numerical approximation. It provides precise, solvable roots for problems that would otherwise be deemed unsolvable. So here, let's focus on this problem to the power 19. To find out the roots of this problem to the power 19, we should first find its corresponding new 19th problem equation. Means we determine the values of SR for the Q relative respectively to LR for the Q, where R in fact here belongs to the set of numbers from 0 to 18. Means we will search S minus 1, we'll search S1, we'll search also S2, S3, up to S18, means 19 minus 1. Traditional methods for solving polynomial often involve numerical approximation, which can be quite error-prone, especially when we are dealing with high-degree polynomial equation like this one, 19th degree polynomial equation. Numerical methods such as Newton's methods give as approximation of the roots, but these come with the risk of rounding errors and can guarantee exact values like we will be doing exactly. But with the Ezouidi theorem, we approach the solution differently. This theorem allows us to break down the polynomial and solve for the roots symbolically. It involves a recursive process that systematically find the exact values of the roots, avoiding any of the errors that arise from approximations. Let's first of all focus on the theorem of Mr. Morat-Sultan-Ezouidi. Here, to start, we should use Morat-Sultan-Ezouidi theorem. This is the theorem of Morat-Sultan-Ezouidi that had been written as or had been written as subscript k minus 1 of the r equals the sum from 0 to k combination n minus r choose k minus r n raised to the power r between parentheses negative 0 for the q raised to the power k minus r times l r minus 1 of the q. So let's see the formula again and explain how it works. Here is the formula that we will use to compute the roots. Let's break it down we'll talk about the theorem, how it works. So we can see that combination and minus r, choose k minus r, these are binomial coefficients that adjust the terms. N raised to the power r, this term raises the degree of the polynomial, okay? And let's say this term, the base coefficient, negative L042 raised to the power k minus r, this involves the base coefficient, okay? L042 adjusted by the power k minus r, okay? We go now step by step, okay? And here also L subscript r minus 1 42 refers to the area terms in the polynomial as we proceed through the recursion. Now let me show you how Ezouidi theorem solves this problem exactly. We begin by expression the polynomial as. Okay, this is the standard form of my polynomial to the power 19. Okay, no matter if you wrote it as x is to the power 19 plus L042 and you change the negative sign by plus, okay, no matter fully. So because you are after that you are going to write L0 is negative. The first term is L0 is if you wrote here plus, so it would be negative L042. Okay, so here we can then apply the recursive relationship and symbol transformation to derive the exact roots. Here is the step-by-step process. First, we express the equation in terms of sk minus 1 for the cube, okay, because these sk minus 1 for the cube will give you the new coefficient of the new 90-degree polynomial equation relative to the original 90-degree polynomial equation, okay, which in fact is a set of symbolic coefficients that we can recursively calculate. These coefficients are based on the coefficient of the original 90th degree from the equation. As we proceed, we calculate each sk minus 1 over q, which directly relates to the roots of the polynomial. The key here is that every coefficient is determined symbolically without any approximations. For this polynomial, we calculate the symbolic roots. Okay, here between parentheses, we calculate, let's say, all the new coefficient of the new 19th degree polynomial equation relative to the original 19th degree polynomial equation, and we obtain that 0, let's say, from 0 to 7, all sk minus 1 vanished, okay, or collapsed to 0. Except, let's say, S8, which is equal to negative 92,377 multiplied by 19 raised to the power 9, and S17 is equal to 823,751 times 19 raised to the power 18, and S18 is going to be equal to 0. Okay, means all the new coefficient vanished or tends to a no, okay, except S8 and S17. Okay, so let's show you how it works and how we found these values. We can use a calculator. Okay, so this recursive calculation of coefficient ensures that we are working with exact symbolic values. Okay, for by convention, we admit that s minus 1 is going to be equal to 1. Okay, when you put here k equals 0, you will obtain 0 minus 1, which is minus 1, means s minus 1 of 42 in fact is equal to combination and choose 0, which is equal to 1. Okay, meaning that s minus 1 of 42 is equal to combination and choose 0, and this one it gives you the 1. Okay, now for k equal 1, we will use the Ezouidi theorem. By using these components, we calculate the values of sk minus 1 over q for each degree from 0 to n minus 1. Okay, here the degree of my polynomial is 19, so 19 minus 1 is 18. You will start from 0 to 18 to get the new 19th coefficient of the new 19th degree polynomial equation relative to 19th original polynomial equation. After, let's say, calculating the coefficient, you are going to continue solving the new and 19-degree from equation and go back to plug into the formula that alpha or sigma, the roots means sigma from 0 to 18 is equal to L0 for Q plus these new x roots divided by 19. Here for k equals 0, we obtain s minus 1 is equal to 1, always. For k equal 1, this is by convention, my kids, is going to be equal to the formula is that the formula combination and choose 1 times L0 for the Q times L minus 1 for the Q, and this one is always 1 plus n times L0 for the Q. Just substitution, we obtain that L0 is equal to negative 361 plus 361. This one is going to be equal to L. We continue. We'll use again also the same formula, the same theorem of Ezouidi, and we obtain that for k equal to, we'll obtain that S1, this is the formula. The formula of S1 is that combination minus combination 1 choose 1 times combination n choose 2 times L0 for Q squared plus n squared times L1. This will give you, let's say, the second coefficient of the new 19-degree from the equation. If you want to plug in this formula, you will see that this seems to be the quadratic formula, okay, the discrete, okay, but here is in fact give you the correct coefficient of this 19-degree from equation, and with just substitution, we'll obtain that S1 equal to unknown. For k equal 3, we evaluate, let's say, and they use the Ezouidi, the Ezouidi theorem, and we'll obtain that S2 here is equal to, and now this is S2, this is the formula that will give you S2, okay, that combination 2 choose 1 times combination n choose 3 times L0 for the raised to the power 3 minus combination n minus 2 choose 1 n squared L0 for the q to the power 1 times 1 plus n cubed times L2. This formula is generalized, means this one will give you the third coefficient of the new 19-degree from equation relative to the original 19-degree from equation. Means here we work recursively. We use the same structure of the theorem of Ezouidi, and we just give the new values of k from 0 to 8 to 19 to 18 to obtain the new coefficient that corresponds to the original one, okay? And after that, we calculated, let's say, S2 here. So you can use a calculator, we figure out that is in fact is a now 0, okay? We proceed when to continue also to find S3, then S4, then S5, then S6, then S7, then S8, then we should find also S9, and we should also find S10 and S11 up to S18, okay? And to rewrite again our new 19-degree from equation. And then we solve it, okay? Here for k equal 4, we will use, of course, the Ezouidi theorem. This is Ezouidi theorem. Just substitute k equal 4, we will obtain S3, okay? And after using this and simplify this theorem, when k equal 4, we wrote it in its simplest form. This S3 is equal to that. This is the general form when k equal 4 for any n-degree from equation, not depends on n equal 19 or 18, for any nth degree from equation. This S3 means will give you the fourth coefficient of this new nth degree from equation if the highest power is n. But here the highest power is not n, is 90, okay? So here, just calculation, my kids, will obtain that S3 in fact is equal to 0. Okay, we move to the next part. We'll also use Ezouidi theorem to find S4. Just put k equal 5, okay? And here is the formula, okay? Is the formula to find S4. So here you can see that highest power is 19. That's why we n choose 5 means 19 choose 5. And from where comes the 4, the 5 here, because 1 plus 4 gives 5. And why it's positive? Because this is even number. No need to make minus, okay? This is positive, negative, positive, negative, positive, okay? And if the number is even, for example, S3 will come as negative combination 3 choose 1, okay, and so on, okay. Here we use this formula, my kids. This one is the general formula to find the fifth coefficient of the new 19th problem equation, and just make substitution for L0, L1, L2, L3, L4, and so on. So this one, this is 19, in fact, not 18, okay? Because the highest power here is n raised to the power 5, n is 19, okay? So we just make calculation, we obtain the S4 is equal to 0, okay? Here to find the seventh coefficient, okay, or the sixth coefficient, we should use Ezouidi theorem again and replace k with 6 to obtain 5. Then try to develop this or expand this and write in its simplest form. When you write in its simplest form, this formula is generalized, it had been generalized to give you the sixth coefficient of any polynomial equation that you are working with. Okay. So here, what's necessary here is to put k or to set k equals 6. To set k equals 6 means 6 minus 1 is 5. Means you will obtain the sixth coefficient of the new 19th problem equation. So you can see this one. Here 5 is odd number, so the first one becomes negative, then plus, then negative, then plus, then negative, then plus. Okay, combination 5 choose 1, then I will add 5 to 1, 6 choose 19, 6 choose 19, okay, and n raised to the power 19 plus here the formula, where is it? Yes, 6 choose 19 is that. Then 19 minus 2 is 17, choose 4, and so on, means this formula. Okay, this one. So after calculating and make substitution, we'll obtain that S5 is equal to 0. I will just make it up, so we can use calculator, your calculator. Yes, this one. Okay, so this one is in fact the sixth value or the sixth coefficient of this new 19th equation, corresponds to the original 19th equation. Okay, so here for k equals 7 means you are going to find the seventh coefficient of the new 19th equation. To find this, you should apply this formula. Okay, put k equals 7, we obtain a 6. And then divide this and expand it and write it in simplest form. After writing it in simplest form, so this formula, I will write it here. This formula, this one, okay, this one will give you the seventh coefficient, and it is generalized here. So for n is 19, we wrote here 19. This is 7, and this is 7. Combination 6 choose 1 is that. Okay, up to n raised to the power 7, L0 for the 6 raised to the power q. Okay, here we calculate this, will obtain that the value of a 6 here is going to be equal to 0. Okay, we continue. We want to find the eighth coefficient, the coefficient number or index at 8. Okay, for this new 19th equation, we will apply again the theorem. This one, the green one, apply it, okay, and memorize it. And when you memorize it, try to figure out or to write it in its simplest form. And the formula had been generalized. So this is a 7, in fact. This is a 7 equal combination 7 choose 1. Why negative? Because this is odd. Okay, this is 8 because 7 plus 1. This is n highest power. Okay, just substitution means from this to this. This one is for 18th degree from equation. This one is a general. Okay. So here we'll just make substitution. My colleagues will obtain that S7 here is equal to 0. We summarize. S0 is equal to 0, S1 equals 0, S2 equals 0, S3 equals 0, S4 equals 0, S5 equals 0, S6 equals 0, and S7. We'll see that from k equal 8, The common, let's say, ninth coefficient will never be equal to n. Okay, so let's see this one, this example. For k equal 9 means we will try to find the ninth coefficient of the new 90th degree from equation corresponds to the original 90th degree from equation. We'll use again the Ezouidi theorem and we'll obtain the formula when after writing it in simplest form. So this one is S8. Okay, 8 is positive, so no need for negative sign here. Okay, so this one is S8. This is a general formula for any integral equation you work with. Okay, has its own new coefficient and has through this formula, of course. Okay, theorem, let's say like a cursive formula. Okay, so the new coefficient, for example, S8, calculated by after calculating S7 and so on, because it's a cursive. Okay, one depends on the other. Whatsoever, the coefficient different, not different, whatsoever. Okay, here we calculated, we find that S8 in fact different to another. This is S8. I will just guess is equal to negative 22,377 and 19 to the power 9. So this one is going to be equal to different to 0. Now we continue for k equal 10 up to k equal 17, or for k equal 10 up to S16 are equal to 0. Okay, let's continue. Here we have to find the 10th coefficient. We use Morat-Tanzil theorem, and the green one I mean here, and you will develop this and expand it, okay, and try to write it in its simplest form. When you write this in its simplest form, S9 is the general formula to find the 10th new coefficient of the new 90 degree equation relative to the original that you started with before. Okay. Here, what's needed now is to simplify this. So this is the formula S9. You see 9 is negative, is an odd number, that's why he is negative, and so on. So this formula from this to this will give you, in fact, the 10th new coefficient of this new 90 degree equation relative to the original 90 degree equation. Means any point to the power n, if you want to solve it, you should find out its corresponding new nth degree equation. Okay, it's not randomly, let's say, had been created a poem, or no, poem has a structure. A polynomial to the power n has its own structure. You can solve it without finding its new nth degree equation. And the new nth degree equation, let's say, will be calculated using the Morat-Tanzil theorem that will give you the new coefficient, the new exact coefficient. Okay, so here, what's needed now, just I'm going to substitute and we'll figure out that S9 here, in fact, is equal to n. Okay, you can use a calculator and figure out the value of S9. Okay, and after that, we want to find the 11th new coefficient. To find the 11th new coefficient, just set in Morat-Tanzil theorem, k equal 11. So 11 minus 1 is 10. So means you are going to find S10. Okay, so S10 is the 11th coefficient. So here, after expanding this theorem and writing it in its simplest form, we obtain S10 is that. Okay, this is S10. This is S10. All of this, but there is something down. Okay, because it's long. So all of this are here. This is S10, my colleagues. Okay, and my students. This is S10. You see, just substitution now, and use a calculator and figure out the value of this. You will see that the value of this one is in fact is equal to n. Clear? We continue to find now the 12th new coefficient of this new 90 degree equation. You should use Morat-Tanzil theorem. Okay, And this theorem I will tell you, yes, is that how it comes here to show you exactly. Okay, or I will put it here. I put it here in Murad Sultan Video Research. What is it? Murad Sultan Ezouidi. Murad Sultan Ezouidi. Murad Sultan Ezouidi for the name. What is it? Okay. 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 Okay, no problem. We continue. Yeah. So here we told that for k equal 12, we'll try to find or we'll write the 12 to the 12th new coefficient. We make, let's say, we write it in lowest form, and this one had been generalized to give you the 12th coefficient. So this is the formula. It's too long in fact, but the learner, the teacher, the student, or the professor has to write it as it is and calculate it, the value of S11 by substituting L0 with 19, L1 with 171, up to L11. Okay, you see, you started with S11, you should finish with L11 of order Q. Okay, here by calculation, this using calculator, we figure out that the value of S11 is 0. Okay, we continue here to find the 13 new coefficient of this new 19-year proof equation. We use Murad Sultan Ezouidi theorem. Okay, this one. And making k equal 13 will obtain S12, meaning the 13th coefficient of the new 19-year equation corresponds to the original in 19th-degree polynomial equation. So here we wrote, let's say, the formula, the generalized formula, as that S12 is equal to that. Okay, and this one will give you, let's say, the 13th new coefficient of any n-degree polynomial equation. If you work with 20th degree polynomial equation, it will give you the 13th new coefficient of relative to the original one. Okay, here just substitution. We'll change L0 with its value, L1 with its value up to L12. Okay, so here we just put this. We calculated and we figure out that the value of S12 here, in fact, is unknown. Okay, we continue or we proceed to find the 14th coefficient. The same will apply or will use the EMST approach. EMST approach means Ezouidi Sultan theorem. Okay, approach. Here the theorem. Okay, we'll try to substitute k equal 14. 14 minus 1 gives you 13, and the rest you should you just the formula and expand it and write in its slowest term. So this is S13 after writing it in its lowest term. Okay, this is 13 after writing in its lowest term. Okay, so this one, this is this formula had been now generalized. Okay, I'm going now to just substitute. Okay, and we'll obtain that the value of S13 here is equal to 0. Okay, means S10 is 0, S9 is 0, S10, 11, 12, 13. 13 are equal to 0. We continue, we construct this kind of polynomial, okay, but the formula is universal, is a standard formula, okay. For any polynomial equation, you should use this theorem to solve it and to see its characteristics and to see the behavior of this polynomial to the power n. Okay, this theorem seems to be the discriminant formula, not a discriminant formula, in fact, but will give you the coefficient of the new nth-degree polynomial equation. Here, just put k equal 15. 15 minus 1 is 14. This it's clear for you. You can expand k for k equals 0 up to k equal 15, and simplify. Also, this one is another formula I've missed multiple times that I invented, but I didn't find time to explain this. Okay, but one time I will do it, inshallah. Okay, so here, this one is very important formula also. So here, my colleagues, we expand and we expanded, sorry, and we wrote it in its simplest form and obtain that this is S14, the the generalized formula, okay, that will give you the 15th coefficient of any n-degree equation because this is generalized formula, generalized theorem, works for any n-degree equation, even 2000, n equal to 1000, 1000. Even if you extend, for example, you have an n-degree equation and you want to extend it for n plus 1, also the same, no change, okay? Means if you extend this polynomial equation, the first root for the extended one is equal to negative 0 for the cube. Take the sum, okay? So here we continue with all this 4 as 14 after calculating. In fact, is equal to 0. You can use your own calculator and calculating from this up to that, okay? Here, now I'm going to find S15. To find S15, just set k equals 16 in Ezouidi theorem and figure out the value of S15 by expanding the theorem and simplify it and write it in its simplest form. Okay, so here S15 is that we simplify it. Okay, you see this one combination n choose 16 minus n combination n minus 1 choose 15 is equal to negative 15 choose 1 times n choose 16. Okay, just simplify the first two terms. The rest not change. Okay, they remain the same. Okay, so here this one is S15. We'll just make substitution and try to find the value of S15. Here substitution and we obtain that we calculate from here to here. We obtain that the value of S15 is equal to n. Okay. We continue. We reach to finish at least 4 or 3 coefficients. Then we make our conclusion. Here to find S16 means you are going to find the 17th coefficient. So we use Mathematicians theorem and try to set k equals 17. Here you can see that S16 is the sum from 0 to 17, n minus r choose 17 minus r, and raised to the power r between parentheses negative by 0 for the cube raised to the power 17 minus r times the coefficient of the original 19 from equation minus lr minus 1 for the cube. Okay, here I'm writing, let's say S16 in its lowest term is that, okay? So it will be combination 16 choose 1 times combination n choose 17 and 0 42 raised to the power 17 up to n raised to the power 17 times n16 for the cube. We start with S16, we finish it with n16. You see 16 even number. That's why here there is no negative sign. Okay, meaning the first two terms, I will just show you this one. You can use even small numbers. The first two terms of combination, negative n choose 17 plus n combination n minus 1 choose 16 is equal to 16 choose 1 times n choose 17. You see? Okay. Here we continue with all that. I will just make calculation and we obtain that S16. In fact, means you will calculate all of this and you will substitute n r minus 1 with their own values and obtain that in fact S16 is equal to 0. Okay, so here we try to find k equal 18, means you will try to find the 18th coefficient. To find the 18th coefficient, just use Mathematicians theorem, okay, and put k equal 18. 18 minus 1 is S17. So here I will try to write S17 in its lowest term. Okay, after expanding this formula, I'm going to write it as that. Okay, so this is S17 is equal to negative 17. Choose the one combination and choose 18. Why negative sign? Because now is odd number. Odd number, the 18th coefficient will give you an odd number here, 17. 18 minus 1. That's why the minus 1 comes here. This formula, let's say, is a general formula to find the 17th coefficient. Even if you work with a linear equation like x plus 0, for example. Okay? For example, x plus 1 equals 0. To find the S17 means you will find the new 18th coefficient. Means you are going to extend this polynomial to the power 18. Okay? X to the power 18 plus, for example, x raised to the power n, 18 minus 1, 17, plus 0, and so on. Okay? Always true, always correct. Means something really has make sense for you to understand. Okay? So here, 17, in fact, we calculated this, all of this is 17. We calculate and we found that, in fact, is equal to, different to 0, is equal to 823,751 raised to multiplied by 19 raised to the power 18. Okay? And the last term, the the S uh, the S18 has to be equal to 0 because we told that from the beginning that L0 plus S0 divided by 19, 19 divided by 19 is 1. That's why it has to be equal to 0. Now I will just put k equal 19. 19 minus 1 gives 18. Then I'm going to expand this and simplify it and write it in its lowest term. Okay, this is 18 even number. So as it is even number, so the positive sign appear. So this is 18 is equal 18 choose 1 positive. Okay, and I'm going to apply this general formula to find the 19th coefficient. This formula comes from this and stop at this. Okay, after simplifying it. So here, just substitution, I will obtain that the value of S18 is equal to 0. Okay, is equal to 0. Now, my colleagues, we conclude or we write again the value of S18. This is the form to the power 19 that we started with, and we wrote its corresponding new 19 different equation that uh, expressed in terms of sk minus 1 for the cube. Okay, and these are the coefficients of my algebraic equation. And now I'm going to write it again. In other words, S0, S1, S2, S3, S4, S5, S6, and S7 are all equal 0. Okay, except S8, which is equal to negative 92,377 multiplied by 19 raised to the power 9. And then after that, S9 equal S10, equal S11, equal S12, equal S13, equal S14, equal S15, equal S16, and equal also S18, which are equal to 0, except S17 is equal to 823,751 times 19 raised to the power 18. So here we continue, sorry, here we continue with that, which this one is. We continue with that. This problem to the power 19, Abel's theorem, fail. Classical method, fail. Newton, fail. Even AI systems, fail to solve this polynomial equation. Okay, and rational theorem root also fail. Okay, so here we continue using Ezouidi theorem and using EMST approach, we told that these the new values of sk minus 1 of the new Nightingale equation. So we can say that in like traditional methods, which often use numerical approximations, Ezouidi's theorem provides a precise symbolic solution. This ensures that the roots we obtain are exact and not subject to the error that arise with numerical method. Okay. So I will write this. You see this one? P of x equal x raised to the power 19 minus S0 for the x raised to the power 18 up to S18. This is S18, not L18. So we already calculated the value of sk minus 1 for the Q, just now substitution. Now let's focus on the term. Let's focus on the term. I'll go down first. Let's focus on the term involving S8 and S17 because they are different to 0, which leads us to a simplified form of the equation. So my equation, this one, has to be written as x times x raised to the power 18 minus S8 minus S8. You can see it here, minus S8 raised to the power x10 plus S17, okay, equals 0. So here, why we put here x as a common factor? Because the last term is 0. That's why x here is a common factor, okay, equals 0. This simplifies further to x equals 0, or x raised to the power 9 raised squared minus S8 for x raised to the power 9 raised to the power plus S17. Here I will try to find the value of S0 and S1. S0 is 0 always, so I will find S1 for the which is equal to negative S8 raised to the power 2 plus 4 times S17. You see here, S1 for the is the opposite to the opposite value of discriminant formula that I already know, okay, the discriminant, okay. And here, so I will go down, I calculate this, so we obtain that S1 in fact is equal, sorry again, we told that S1 we calculate S1, so it will be, okay, it will be 8,530 or 8,530 billion 215,125 times 19 raised to the power 18. So this one is a huge number, okay. So I will try to find the value of s of x raised to the power 9. Okay, I will go down. Here x9 is equal to s8 for the r plus negative root of negative s1 for the r divided by 2. So this is x9. So xk from 0 to 8 is s8 plus negative root of negative s1 for the r divided by 2, all raised to the power 1 divided by 9 times exponential 2ki pi over 9. Just substitution here, and we find that xk is equal to negative 92,377 times 19 raised to the power 19 plus root of 8,530 billion 215,125 times 19 raised to the power 18. You see 19 raised to the power 18 comes here. Okay, it will be raised to the power 19. It will be 19 raised to the power 9, and then it has to be 1 over 9. So comes exactly equal 19 times negative 92,377 plus negative root 8,530 billion 215,125 divided by 2 exponent to the power 1 over 9 times exponential 2k I pi divided by 9. So this one is the xk. To find now the alpha or sigma k, my kids and my colleagues and my professors, you just make substitution. Okay, so alpha or sigma k from 0 to 8 is L0 for the cube plus xk from 0 to 8. So this is the formula. Okay, just I substitute xk with that. And immediately I replace it with L0 is 19 and xk is that. Okay, divide by 19. You see 19 divided by 19 will be disappear. So the last answer from, let's say, the roots here, double root in fact, because or conjugate root. Okay, here from 0 to 8 we have 1 plus, because 19 divided by 19 is 1. Then 19 divided by 19 times this, it remains only the value that is ninth root of this ratio multiplied by ninth root of 1. Okay, and the last answer for k equals 0, we obtain that L0 for the q, which is 19, xk is 0. Okay, because we told that x equals 0, or I'll come here to get the point. We told before this. Okay, we told before this, you see, x is equal to 0 or this is equal to 0. Okay, so x equals 0 means that 0 is equal to 0. So the first rule that is clear for you is 19 plus 0 divided by 19 is 1. Okay, like that is 1. Okay, now we obtain, let's say, the 19th exact simple roots without approximation, without guesswork, using Murat Sultan Ezouidi theorem. Thank you for listening, and see you inshallah next time. So next time I'm going to make a presentation for advancing solution to high degree problem equation and Abel curse approach via Ezouidi theorem. Okay, so this one is an article in fact. Okay, so here I'll just close this one. Okay, I'll come to YouTube. Okay, thank you for listening, and see you inshallah next time. I'll check here it works. Okay. Yes, okay, now thank you for listening, and see you inshallah next time. Okay, goodbye.